In this video, we will finish working our way through Lab 1 Part 2 together. Now, at the end of the last video, I actually quit Mathematica, went out and did some other stuff, and now I'm back to finish making this video and finishing the work for Lab 1 Part 2. And that's actually a fairly common thing that students do. There's nothing wrong with stopping in the middle of a lab, saving your work, going out and doing something else, and coming back to finish the lab later. There are some things that you need to be aware of when you do that, and we'll see that in just a minute. So if you do not already have your Lab 1 Part 2 notebook up on your computer screen, please open your copy and scroll up to the top of the notebook. Now that you've done that, I want to kind of scroll through the notebook together to find what we did on the last video and where we need to start working this time. So we just scroll through and we say, yeah, we did that, and I did that, and I remember that sort of stuff, and I remember making F of that. That output is there, and there's some more output. I remember making this graph, and I remember that in question 1 we had to talk about the symmetry, and yeah, my answer to question 1 is still there, and then we had to find some roots, and my answer to question 2 is still there. And where I quit working was I didn't want to start the derivatives into integrals. So I now know that I'm where I want to start working. So in your Lab 1 Part 2 notebook, I want you opening up the section called derivatives. Now you'll notice that the first thing is we want to stay working with the same function, x times cosine of x squared. Now, because it's early in the semester, I tell you to please activate the cell below just to make sure the function hasn't changed. So I put the cursor in that cell and I activate, and lo and behold, bad things happen. It shouldn't be saying f of x, it should be saying x cosine of x squared. When Mathematica does this, that means Mathematica has no idea what function you're talking about. And the most common cause of that is that you quit Mathematica and you're now starting to work afresh. And Mathematica does not remember everything from the previous session. So the fix for this kind of a thing is real easy. You simply scroll all the way back up to find the cell where the function was first defined. And that's the cell here. Put the cursor in that cell and then do the shift return to activate it. Then come down to the cell that is not working and reactivate it and see if it fixes the problem. And most of the time, this will actually fix the problem. So now we have the right function in front of us. So at this point, what I want to do is I want to start thinking about taking derivatives. In a Calculus 1 class, we would take the derivative of this function using the product rule and also the chain rule. And since all of you have already taken Calculus 1, you ought to be able to do that by hand. And if you want to, you can stop the video and you can find the derivative by hand. But the point of this course, of course, is that we don't have to find the derivative by hand. We can make Mathematica find the derivative for us. And Mathematica can use either a prime notation to get that prime. That's the single quote on the key that is next to the return on most keyboards. And if you put the cursor there and press shift return, you get the derivative. If you prefer Leibniz's d dx notation, it looks like this in Mathematica. The first d is the d up here, and then the d and that x is the dx here. So this is take a derivative of f of x with respect to x. And you'll notice that it's the same thing. Now, if you're trying to evaluate derivatives, this one is usually much easier because all you've got to do is put the number in for x. So f prime at 1 is cosine of 1 minus 2 times sine of 1. This, of course, may not make a whole lot of sense to you because that's the exact value, and the 1 here is 1 radian. 1 radian is a little bit less than pi over 3 radians, so I have an idea of what that is. But why bother trying to figure it out in my head when I can easily just hang a capital N around it and make Mathematica do it? So Mathematica tells me that the slope of the tangent line, f prime at 1, is going to be minus 1.14264. So at x is equal to 1, the tangent line is going to have a negative slope. Of course, a classic Calculus 1 problem is drawing tangent lines. This input cell here gives all of the information that you need for making Mathematica draw a tangent line to a curve. You'll notice that we're going to clear the word tan line because I'm going to use that for the name of my tangent line, and x our variable. And we're going to make the tangent line a function, so that underscore is mandatory. And this function is going to be f prime at 1, because the point of tangency is x is equal to 1, times x minus 1 plus f of 1. This particular expression is in point slope form for the equation of the tangent line. And the point of tangency is 1, comma, f of 1. And then finally, the plot command puts everything together. The semicolons say, don't give me any output from those particular input lines. So we activate that cell, and lo and behold, we are certainly looking at what is plausibly a tangent line relationship. If I don't want all of this stuff and all of this stuff, I can easily zoom in much closer to the point of tangency. And when I do, I can see that, yeah, here's the curve, there's the tangent line, and that certainly looks like a tangent line. I want you to stop the video and read question 3 and think about how you would do question 3, part 3 on paper. When you've done that, start the video back up and we will work through question 3 together. And you should type this stuff into your notebook, if need be, by stopping the video and then typing exactly what I've typed in your notebook and doing the same kinds of things with me. So first of all, I want to create an input cell, and I want to define the function g of x. So I will clear g and x, and then I will make g a function of x, and it's going to be x times sine of x. And you will notice that I'm using proper function notation. There's the underscore, I have a star for the times, and I've capitalized sine. If I want to, I can double check that I've got the formula right, and yes, I have the formula right. Part 2 is simply asking for the derivative, so I can say g prime of x. If I want to, I could say d g of x, take the derivative of g of x with respect to x, and I get the same thing. Now, the third part of this is the hard part. It says, have Mathematica make a plot that shows both the function and the tangent line at x is equal to pi over 3. Now, there's a hint here that says copy, paste, and edit the cell that I use to both define and draw the tangent line. That's a really important major hint. I would not expect a new Mathematica user to know how to write this cell right from scratch. But we know this monstrous mess generated the right kind of picture. So I want you to select the cell bracket for that particular input cell and copy it. Now, you can do it with a keyboard shortcut of a Command-C on a Macintosh or a Control-C on a PC, or you can use the Edit menu and do a copy. Now that it's copied, I want to scroll right down to where I want to put it, which is below part 3. So get the cursor to be a horizontal I and click the mouse to get the horizontal line. And now do the paste. So I'm doing a Command V because I'm on a Macintosh. It would be a Control V on a PC, or you could always use the edit menu. But now we have to edit this cell. The name of the function is no longer f, its name is g. So all of these f's get changed to g's. The point of tangency is no longer 1. The point of tangency is pi over 3. So all of the 1's have to be changed to pi over 3's. And you will notice that the pi is capitalized. Now, I also have to think in terms of where do I want to make the plot. Well, let's just try 0 to, I don't know, pi for the time being. And yeah, that plot would do pretty decently. If I want to get the point of tangency in the middle of the plot, well, pi over 3 would be halfway between 0 and 2 pi over 3. And the neat thing about this plot is it's showing that the tangent line is crossing the function. And what that actually is saying is that pi over 3 is an inflection point for the function x times sine x. I can pick that up visually. I would never know that right off the top of my head without this graph. So now what am I doing? Well, let's see. Let's save our work. Again, I'm not going to continue putting this in all labs, but it's something that you want to remember to do. Now, Math 163 is primarily about using Mathematica to solve Calculus 1 type problems. But because most of the students in my Math 163 class, the transfer section, have also had Calculus 2, I want to go ahead and introduce you to the integral command because you might be in a math course where the need to integrate functions is something that comes up on a regular basis. So let's look at integration in Mathematica. Well, we're going to continue looking at f of x is equal to x times cosine of x squared. So I'll make sure that my function hasn't changed. All right, it hasn't changed. Now, Mathematica has a very powerful integration command. It knows all of the rules about integrating and can apply them repeatedly, and it has a bunch of special kinds of formulas that are inside its integration package. Basically, if there is a so-called closed form for the antiderivative of a function, Mathematica can integrate it. The integrate command's name is integrate, and the syntax is pretty simple. It's integrate, what do you want me to integrate, and what variable am I integrating with respect to? So this is the integral of x times cosine of x squared. Now, x times cosine of x squared is easy to integrate. That is just a basic u substitution. And if you want to, you can stop the video and integrate it by hand, and you'll get this. Now, you should notice that Mathematica does not add the plus c. And the reason why is that it was a programming decision. Lots of functions, however, do not have closed forms for integrals. If I'm wanting to integrate the cosine of e to the x squared plus 1, and I just tried the integration command, Mathematica spits the integral right back out at me. What this is Mathematica is telling you that there's no simple symbolic way to write the antiderivative of this function. But the best you can do is to throw an integral sign around it. Sometimes if you're trying to integrate something, you may get an antiderivative, but it may involve a function that you've never heard of. And what this is telling you is that there's no easy symbolic antiderivative, but the function crops up enough where mathematicians have defined the antiderivative as some particular name of a function. Okay, so indefinite integration is pretty easy. Mathematica can either do it, or the problem can't be done, and so Mathematica can't do it. What about definite integrals? So let's look at definite integrals. We'll continue working with x times the cosine of x squared. So there it is. Now I can find, here's a definite integral, and I can find the value of it with the integrate command. You'll notice that the second argument has changed. Instead of just being a single x, we now have a curly q x comma 0 comma 1 followed by a closing curly q. The way to read this particular input cell is that we want to integrate f of x with respect to x between 0 and 1. In other words, the lower endpoint is the first number and the upper endpoint is the second number. Put the cursor in that cell and activate it, and you get the exact number. The exact value of that definite integral is sine of 1 over 2. Now, if you want a decimal equivalent, you can hang the capital N around the integrate command. And so there's the value of the definite integral. Or there's a special built-in command called the InIntegrate command, which has the same syntax as integrate. What do you want me to integrate? What's the variable of integration? And where do you want me to start and where do you want me to stop? If we activate this cell, we get the same answer as we get there. In general, InIntegrate is a more reliable integration command because it uses a numerical technique called Simpson's rule. And in Math 162, we'll have a sequence of labs that look at Simpson's rule. It's important to understand that if Mathematica cannot integrate the function, that doesn't mean the definite integral does not exist. If I plot this ugly function between 0 and 1, I get a very nice chunk of area. And so I know that the integral between 0 and 1 of h of x it exists and it's a nice number. In fact, it's got to be a positive number. I can't find the exact value because Mathematica can't integrate the function. However, if we use InIntegrate, Mathematica can tell me that that chunk of area that we were looking at is 1.11282. So the area underneath this curve is approximately 1.11282. Now, question 4 is the last thing in this notebook. I want you to stop the video and I want you to read question 4 and then start the video back up and we will work through question 4 step by step, and you can copy what I'm typing in my cell, in my notebook, into your notebook, and you can stop the video to get the typing right anytime that you need to. So let's see. The first part of the question is asking us to create an input cell and define g of x using the correct syntax. Now you may recognize that we've already done that. So since we recognize that we've already done that, we can scroll backwards and we can say, let's see, we did it right here. So let's select that cell, copy it, and bring it down to where we're doing our work. And I don't even have to do any editing this time because I'm on the same function. And just to double check, I'll ask it for g of x. So yeah, I've got the right function. Now, if you want to try and integrate x times sine of x by hand, you have to use integration by parts. And if you really want to do that, you can stop the video and you can do it in your notes. But I also want to have Mathematica find it for you. So in this particular one, I'm simply going to say integrate the function that I want to integrate. It's now g of x, and I want to integrate with respect to x. And the answer is going to be minus x times cosine of x plus sine of x plus any constant that you want to add. If you take the time to integrate this by parts, that is indeed what you will wind up getting. Well, let's see. Let's have Mathematica make a plot that shows this guy over a particular interval. Now, I can actually do that without copying and pasting. I want to plot g of x, and I want to plot as x goes from 0 to pi over 3. And yeah, that's a nice chunk of area. And this definite integral is equal to the area underneath that curve. So let's put that in a text cell. Yes, that definite integral is well defined because the area under the curve exists. Now I want to simply find the exact value of that area. Well, that would be integrate. What do I want to integrate? Its name was g of x. I want to integrate between 0 and pi over 3. And that is the exact value, and you'll notice that it has a square root of 3 in it, so this is an irrational number. If I want to have a decimal equivalent, I can simply do InIntegrate. And it's the same range. And so that chunk of area, this chunk of area here, is approximately 0.342427 square units. You should definitely save your work. And at this point, once you have finished the work on this notebook, you should turn it into the appropriate Dropbox and then go on to part 3 of Lab 1. Now, part 3 of Lab 1 does not have a video, so what you need to do is read through that notebook very carefully and follow all of the instructions, and when you're done with it, turn it in through the Dropbox. If you have questions, just see me in office hours.